Hello everyone, welcome to the video today. Are you noticing anything different? Does it sound different to you? More soothing, perhaps? Well, guess what? We've classed it up. Old Redbeard McFreckleface decided to go out and actually buy a microphone, so hopefully I won't have to shout into the videos anymore and make it sound like I'm even more salty and angry than I normally am. Though I do get salty from time to time in these videos, but hopefully this will improve them just that much more. So in these videos, we're going to be talking about the last thing that we're going to be learning in this unit, which is called solids of revolution. So we've learned how to find areas of enclosed areas, we've learned how to find arc length, and we've learned how to find volumes of solids by a method of slicing. So now what we're going to do is another type of method of finding a volume, and that's by taking an enclosed region where you can see right here we have the enclosed region, we have the enclosed region R. And so what we're going to do with that enclosed region is pretend that the x-axis in this case, on this one to the left, the x-axis is an axis of rotation. I can spin this region R around that axis, and it's going to end up forming a solid. Now, those of you that have ever been in like pottery class and been behind the wheel, I kind of equate this to doing something like that. You're kind of just molding this shape by spinning a particular area 360 degrees. Now, over here on the right, we have another situation where we have this circular region right here, and in this case, we're spinning it about the y-axis. Now, the difference you'll notice in these two shapes is that the one to the left is going to be a solid shape, a solid volume. The one to the right is going to have a hole in it, so it looks kind of like a donut sort of shape. And these reflect two different methods that we use to calculate these volumes by these methods of revolution. So basically in this video, we're just going to discuss kind of the strategy of how to solve these sorts of problems. And in the next video, we're actually going to do some example problems. So no example problems in this video. It's just going to be me talking in my now very soothing voice. Okay, so that's probably not soothing, that's probably really creepy. Okay, anyway, so the first method is a method called the disk method. So this is when we start out with a region. So in this case, you can kind of see they've outlined this region right here. Okay, so that area looks like this. Again, we're spinning it about the x-axis, and because we're spinning this about the x-axis, that region, which I just shaded in black, is actually in constant contact with that particular axis. So therefore, when we spin it, we get this solid looking shape that we get right here. And then what we do to figure out the area is we do another volume by slicing method. Remember, this is kind of like a slice. So this slice is going to have a particular radius. And so if we want to find the volume of this particular slice right here, that volume will be the area of that cross section, which will be pi r squared times, they called this delta x right here, times the thickness delta x. So if we change that delta x to be a dx, meaning it's very, very small, and we take a function, let's say one like this one right here, where that radius of our cross section, depending on where we are, is going to vary. So we'll call that r of x squared, put a pi in front. If we integrate that between 2 points A and B, that's also another way that we can find the volume. So basically this is just really applying the volume by slicing method to cross sections that are always going to end up being circular. The reason is because we're rotating them about an axis. They end up forming circular cross sections. So again, the disk method is called the disk method because if we look at this little slice of volume we're getting, it's always going to look like a disk, like a coin. It's going to be a solid shape that's like a tiny, tiny, tiny little cylinder. So if we go through here to look again, this is what I was talking about before. Now in this case, it looks like between A and B, I have a region which is bounded by this black line, which I am drawing right here. I'll try not to go over the yellow. But the radius of that black line for any cross-section, this yellow cross-section, is just happens to be, if I chop this thing perpendicular to the x-axis with a machete at this point x right here, we would get a circular cross-section. Now let me use a different color. The radius of that cross-section will be given right here. Notice though that that radius is just going to be given by whatever this function is. That's the length of that radius line right there. So if we want to calculate the area of a cross-section, that'll just be pi times that radius squared. And if we integrate from a to b, then that's going to give us the volume of that solid. Again, remember that in this case, pi r of x squared is actually our area function if we go back to volume by slicing. So like I said, we're just applying the same method, but just in a specific case when we're always going to have circular cross sections. Okay? And so if we apply the disk method, this was the case where we applied the disk method right here, this formula right here. When we applied it when we were looking at cross sections perpendicular to the x-axis, but we don't have to do that. We can also rotate things about the y-axis. And if we rotate about the y-axis, or more specifically, any axis that's actually perpendicular to the y-axis, we can actually add that right here, rotating about, and I'm sorry, not perpendicular, parallel. I said the wrong thing. An axis parallel to the y-axis, then we can just apply the same formula. So when we switch from dx to dy, that's going to be dictated mainly about what axis we're rotating about. So if we're rotating, let's say, about the x-axis or about the line y equals 2 or y equals -5, those are all lines that are parallel to the x-axis. So if we did that, we would be using x values and we would be using dx. Now if we instead rotated about the y-axis or about the line x equals 2 or x equals -3, then we would have to use the dy method. And notice when we use dy, our limits of integration become y values, and our radius function must be a function of y, not a function for x. So if we're going to go dy, we got to make the commitment to change all x stuff to y stuff. Okay? So basically, to reiterate, we use the disk method again when the area that we're trying to revolve is in constant contact with the axis of rotation. And we can either use the dx or dy method there based upon if we're going to be rotating about a line parallel to the x-axis or parallel to the y-axis. So the next method in solid of revolutions is called the washer method. So remember that we said in the disk method we want our area that we're rotating to be in constant contact with the axis of rotation. Well, look over here to the right. We see that, let's say in this case, we were rotating everything about the x-axis. Well, in this case, our area, this shaded area that we're rotating, that is not in constant contact with the x-axis. In fact, it's not in contact with it at all. So if we rotated it about that axis, the shape that we would end up getting is this washer shape right here. So remember, before we had a disk, but now because we're not in constant contact with that axis of rotation, we're going to have that hole in the middle. Now, if we translated that out to rotating the entire shape around, we would get this thing, which I don't even know what to call that. To me, it looks like something you would put on like a baby's formula bottle minus the rubber nipple. That's a pretty terrible description, but that's literally all I can come up with right now. So that's the best you're going to get. So in this case, notice we have two functions. They're very hard to see, but this upper function right here, we called that g of x, and the lower function right down here was called f of x. So if we want to find the area enclosed by this washer right here, all we got to do is take the area enclosed by the disk and subtract the area of the hole on the inside. So the outermost disk is going to have that radius, which we called here g of x. The innermost disk is going to have the radius f of x. So what you can see is what we did right here. When we integrated, remember our cross sections, we're still saying they're circular, but in this case, pi times g of x squared is saying take the area of the big outer disk and then subtract it from pi times f of x squared, which is the area of the inner hole right here. So if we take the area of the disk, subtract the area of the hole, we end up getting the area of the particular cross-section. And again, as we've seen with volume by slicing and with the disk method, if we integrate this over our two limits of integration, we're going to be able to actually find the exact volume of that particular solid. So these are two pretty cool methods. They're ways that we can find volumes of shapes that we have not been able to previously find before. So pretty cool stuff. So here, if we're talking about the washer method, again, we're going to be using the washer method when the area that we're revolving is not in constant contact with the axis of rotation. In this case, what we have to do is define an outer radius, meaning this is the curve furthest from the axis of rotation. So to visualize this, let's say we had a curve from A to B, and it looked like this, and we were rotating about the x-axis in this case. Our outer curve would be this, because that's the furthest distance from that point, and I should probably draw the inner curve first before I describe this stuff, but our inner curve would be that guy right there because it's the smallest distance away from our axis of rotation. Okay, so that's how you can define the outer curve and the inner curve, and then you're basically just applying this formula to figure out the volume using the washer method. So I would say the most difficult portions of these problems are really just determining what is that inner radius, what is that outer radius, and also realize that in the washer method we can also swap everything and use dy. Okay, so in that case, remember, we use dy if we're rotating about an axis parallel to the y-axis. We use dx if we're rotating about an axis parallel to the x-axis. So if we want to come up with some kind of end-all, be-all way to think about how to use these, and these, what I would recommend doing in this video, write these rules down. And when we get to the next video, you can apply these rules, and you'll see that if you just go through asking yourself these two questions, you're putting yourself in a very good position to be able to solve any volume of revolution problem. So the first question you want to ask yourself is, you want to find out if it's a disk or a washer. And the way you find that out is look at your region that's rotated. Is it in constant contact with your axis of rotation? If it is, use the disk method. If it's not in constant contact with your axis of rotation, use the washer. Now you could get a situation where, let's say, we were rotating about this line and your area looked like this. Now, as you see, between here and here, that area is in constant contact with the axis of rotation, but then after that, as we move along this way, the area is not in constant contact. So in that case, you would actually split that up into like a half disk, half washer sort of thing. Okay. Now, the next thing you want to decide, the question number 2, is going to be, what do I rotate this thing about? So, remember, if the region is rotated about an axis parallel to the x-axis, we use dx. So therefore, if we're using a disk method, this would be the integral we would want to solve. If we're using the washer method, this would be the integral we want to solve, remembering that difference between the outer and the inner radii of our kind of ring-shaped cross-section. Now, if we have the opposite, if the region which we're rotating about is parallel to the y-axis, we use dy. And then our equations for the disk method become this. Our equations for the washer method become this one. So like I said, just write down really this stuff on this last slide. It'll help you out tremendously. And in the next videos, we're going to go over a couple example problems. And hopefully once you see those, you'll be totally up to speed on this stuff and realize that they are very formulaic. And once you understand the formula, you pretty much understand how to solve the problem. So I will see you in the next video.